Hey guys, how's it going? Today we're going to be talking about exponential growth, the natural base E, okay? To be more, descriptive of what I'm talking about, let's go ahead and write the function. We're talking about y is equal to a times e to the x. Now the a value, that is a constant, all right? And the e, that's actually a number, okay? It's kind of like how we talk about pi. We say that pi is like 3.14 and it keeps on going. Well, e represents a number. It represents the 2.7 and it just keeps on going and going and going, okay? So please understand that e is not a variable. A lot of students will think we've got 3 variables here, but actually we've got 2, and actually just 1 really. It's just the x is the variable and the a is the constant and e is a number, okay, is a constant as well. Now, when we talk about the a value, if the a value is greater than 0, all right, what that's going to do to our graph is it's going to make it go into a very positive slope, okay? It's going to be rising up. Now, the key point for a natural base e function is it passes through the point at 0, 1, and it will slowly increase like this. Now, once again, there is an asymptote right here in which it cannot cross, okay? It'll get close to it, but it will never cross it, okay? Now, also something to note is that the r value, okay, not only does a have to be greater than 0, but the r, okay, has to be greater than 0. And that's a key point, is that the r has to be greater than 0 and the a has to be greater than 0 for the graph to look like this. Now, once again, we have another type of function, but this is going to be decay. Now, this is when the graph slopes downward, and we have y is equal to a e to the x. So the overall function doesn't change. And you'll notice even a is greater than 0, but r, okay, r is less than 0. And because the r value is less than 0, that causes the graph to slope downward. Okay, but it's not going to go ahead and pass that asymptote once again. It'll get close to it, but it will never cross it. And the asymptote is, of course, the x-axis, okay? Now let's go ahead and talk about some examples and maybe kind of get you in the mindset of what I'm talking about in terms of a and in terms of r. So let me go ahead and shift down. Alrighty, so here's an example. So it says, tell whether the functions represent exponential growth or decay. Now, of course, when I posted this onto the little app, it took away some of the examples. So let me go and write them in. So say if I gave you y is equal to 3 e to the x. Okay, so looking at this function right here, we would say that this is a growth because first and foremost, if you look at the a value is greater than 0. And if you look at the r value is 1 because that's a 1x. So the 1 is greater than 0. So with those two bits and pieces of information, we say that this is a growth function. Okay. Now, let's take a look at the flip side. Say I gave you like a f of x, switch it up a little bit, is equal to e to the negative 0.5x. So looking at this, the a value is greater than 0 because it's 1. But if we look at the r value, okay, the r value is a negative 0.5. With that being said, that is going to be less than 0, right? That's not greater than, that is definitely less than 0. So what this would end up being is decay. Okay, so since 1 is greater than 0 and negative 0.5 is less than 0, we have decay. Now let's keep going. Let's do some more examples. So say I have y is equal to 1/2, okay, e to the x. Take a second. What is that one going to be? Is that growth or decay? Well, in this case, it's going to be growth because 1/2, that's still greater than 0, right? It's small, but it's still greater. And also, too, the r, what is it? It's 1. That's also greater than 0. So this is clearly a growth. Now, looking at the next one, let's try this one. We have y is equal to 4e to the negative x. Well, 4, that's greater than 0. And let's see here, what is r? Well, r is a negative 1. Now, oops, wrong symbol. That's less than 0, right? Negative 1 is less than 0. And so since that is true, we have a decay. All right, so hopefully that kind of gives you an idea of what we're working with and how these problems will look in terms of a graph, okay? So now let's go ahead, let's continue to move down on this paper and see what else we're gonna kind of look at. All right, here we go. So the reason why we talked about those formulas a second ago is because we're now gonna be talking about continuously compounded interest, okay? Now, the continuously compounded interest very much follows closely with, okay, the natural base E formula. Because if you look at it, you end up having A, also known as the Y, right, is equal to the P E R T. Now, a lot of people will reference continuously compounded interest as PERT. You can see why they call it PERT. They literally just kind of sound it out. But let me describe each one of these variables. So this first one right here, this is just the initial value. That's that A value that I was talking about where it was greater than 0, like a 1 or a 1/2. Okay, that's your initial amount. Now the E, remember I said it's a constant. It's not a variable. We know that to be an actual number. So keep in mind that this is a constant number. The R, of course, it's rate, right? I mean, that just kind of makes sense. And then the T, you can kind of guess that is, of course, time, like in most cases, okay? So that kind of hopefully describes what you're looking at there. Now, looking over at the example, let's apply it. It says Marvin opened a savings account and deposited $400. Now, that $400, okay, you can probably guess that that is yes. That is the amount, okay, in which, and let me go ahead and scroll down just a little bit. 1 second. There we go, so I can see everything. That is the initial amount, right? Now, it goes on to say that he earns 14% interest, and it's compounded continuously. Now, this phrase, compounded continuously, is important because it separates it from what we talked about like in the previous notes in 7.1 when we said it's compounded quarterly or compounded daily or compounded monthly. If you see the phrase compounded continuously, you need to think of PERT, okay? Does that make sense? That's kind of where this phrase is important, okay? Now, it goes on to say if he wants to use the money to buy a bicycle in 2 years, okay, that 2 years being the time, okay, how much will he be able to spend on the bike? So we're going to go ahead and utilize this information, right? So you end up having A is equal to 400, okay? E is a number, okay? And raised to the R. Now, it's 14% interest, right? And also something to add, it earns, okay? Like, I don't know if anybody sees this phrase, but earns 14% interest. Now, in order for you to earn this interest, okay, it's going to be a growth function, right? We're going to see that it will grow, that this is going to be a number greater than 0, right? And so when you go to write it in, it's going to be positive, so it's going to be 0.14, okay? And then, of course, the time in which it undergoes is 2 years. And so we just plug that into the calculator, and you should end up getting $529.25. So it gains interest, right? $529.25 is the official amount of how much he will be able to spend on the bike. Now, something to understand is in your calculator, you actually have the E function built in. You're going to have to look for it, okay? In most scenarios, it's located on the left-hand side of the TI Inspire, if I'm not mistaken. And for other calculators, you might have to click the shift button. It's probably, the secondary color of your calculator, where you're going to have to click the shift and then click the appropriate button. So definitely look for it. It will make your life easier because you can type it in just like we did right here for the problem, 400e raised to the 0.14 times 2. And that'll give you your answer, okay? Alrighty, let's look at example number 2. Example number 2 says that we have Ava puts $200, okay? And I'll go ahead and highlight some stuff. $200 in an account. She uses for school expenses. The account earns, okay, 1% interest and is compounded continuously. And it's across 6 years, okay? So let's go ahead, do that problem. So we have A is equal to 200. That's the initial amount that she put in for her school expenses. The school expense, or the amount that she put in, is going to earn an interest of 1%. Now that's 0.01, not 0.1, right? 0.1 would insinuate that it's 10%, and that's going to be multiplied across 6 years. You plug that into your handy dandy calculator and you should get $212.36. Make sure you put units, okay? All right, there you go. Now, let's look at other types of exponential functions, because there are some other types. So let's take a look at those. So for these other types, okay, these are more or less used for when we're talking about like things that grow very quickly, kind of like bacteria. That's example number 1. We've also used them in terms of carbon dating and things like that for material that decays at an exponential rate. So let's kind of talk about how we utilize those. Now, for this one, for other exponentials, okay, you have A is equal to P times M, okay, to the little t over big T, okay? And I'm going to describe this as best I can. So the A value, okay, that's just what the initial amount's going to be, and that's the P, right? So that's still initial, okay, what you start off with. Now the M is the multiplier. This is when equations will go ahead and say things will double, things will triple, things will quadruple. That's what the M is referencing. Now the little t is time observed. Okay, observed. And then big T, that's going to be time required for growth. Okay, time required. And then I would put for growth if you got space. So these T's both reference time, but in how you utilize those constants is going to be important. So for example, let's kind of take a look at example 1. It says if the number of bacteria in a colony triples, okay, so that's the multiplier that I was talking about. So the colony triples every 12 hours. There's currently a population of 5,000 bacteria. What will the population be after 1 day? Okay. Now, looking at this right here, okay, the time that we're observing, okay, this bacteria is across 1 day. Does that make sense? So the time we're observing is 1 day. The time required for it to go ahead and triple is 12 hours. Okay, hopefully you can make that distinction, okay? Is that time observed, okay? And we'll call it time O. That is 1 day. Now, please understand something though. The time required, T time and then R, that is 12 hours. We're talking in terms of hours. And you have to make sure your units are consistent across the board because you can't have hours over days unless you really understand what you're trying to communicate. I would stay away from trying to do that you should make sure your units are all consistent with one another so they can communicate effectively. So if I'm saying that the time required for this bacteria to triple takes 12 hours, then when I'm talking about my time observed, I should try to get that time observed also into hours. So when you talk about a day, how many hours are in a day? 24 hours, right? There's 24 hours in a day. So with that being said, when you go to write your T over big T, you should write it in terms of hours. You shouldn't write it in terms of, your 1 over 12. Because if you do that, you're going to put that into your calculator and get something completely different, okay? Now, of course, the p-value, that's going to be 5,000 because that was the initial amount of the bacteria, right? And then the multiplier, the m, is triples, so that's a 3. So if I were to say doubles, that would have been a 2. If I would have said quadruples, that would have been a 4, and so on, okay? So looking at this right here, you would have A is equal to 5,000 times 3, because now it's a multiplier, okay? And that's going to be from 24 over 12. And you plug this into your calculator, okay? Use the caret symbol to go ahead and put the 3, or put the 24 over 12. That's that rational exponent stuff. And so you have A is equal to 45,000 bacteria. Okay. Alrighty, there you go. Now, there is other things such as this half-life model, so let's kind of scroll up for that one. So when we're talking about half-lives, okay, that's going to be A is equal to P times 1/2 raised to the t, little t over big T. Now, little t over big T is actually the same. It is the time observed. So it's still time, but that's time O. And this right here, is time R, okay? That's the time required for growth. This right here is the initial amount, yes, P, and then this 1/2, of course, is the constant, right? It's a 1/2 that's going to stay because these things decay by half over a certain amount of time. So when you look at this, it says in example 2, you have 240 grams, okay, so let me go ahead and break out my highlighter. You have 240 grams, that's our initial, of radioactive form of carbon. If it's half-life, this phrase right here indicates the 1/2 over here, okay? And it says they're 20 minutes, okay? How much in grams will be left after 1 hour? Okay, so we're observing this over 1 hour. The time required for it to decay is 20 minutes, okay? So looking at that right here, we have, let's start with the P. P is equal to 240. Then your big T and little t. So little t is going to be your 1 hour. Now we should communicate that in the proper units because big T is in 20 minutes. So how many minutes are in an hour? 60. So then when you go to analyze this, you have A is equal to 240, and then you have 1/2, right? Because that's a constant. And it's 60 over 20. And so A is going to equal 30 grams, okay? So in exactly 1 hour, you'll go from having 240 grams to 30 grams, okay? And that is it for this video. Let me know if you guys have any other questions, and let me know if you have any other interests or want to understand its other forms a little bit better. I'll be posting the homework very soon. Alrighty, bye guys.